And this is very exciting because it is pretty much almost 35 years since the discovery of high harmonic generation. So it tells us the time period that it sometimes takes to find application for new light sources. Short wavelength light in the extreme ultraviolet and soft X-ray region of the spectrum gives us unique capabilities for probing materials. The light can penetrate through opaque materials. It has inherent sensitivity to what element is in the material, its chemical state or its magnetic state, because the position of absorption edges moves around depending on that state. It can be non-destructive as a microscopic imaging technique, and because of the short wavelength and high frequency of that light, if you can make coherent beams of short wavelength light, then one can make a microscope that can image at the wavelength limit in 3D, and because of the high frequencies, can capture any dynamics relevant to function. Of course, X-ray technology has had broad impacts on science and technology, all the way from security to medicine to science. X-rays were used to capture the double helix structure of DNA, for example. But when it comes to imaging, the technology that's in widespread use is basically an X-ray light bulb, a more powerful version of the X-ray tube that Röntgen developed at the end of the 1890s. And so for that reason, if we look at an X-ray image, the crispness or spatial resolution of that image is nowhere near the wavelength of the X-ray light, because basically one is taking pictures with an X-ray light bulb. So why not make an X-ray laser? So it turns out that the power requirements to build an X-ray laser based on population inversion are simply too challenging for widespread use. We've known from the time of Einstein what the ratio is between the spontaneous and the stimulated emission coefficients. That scale is the frequency to the third power. And we can use that simple scaling to make a back-of-the-envelope calculation for how much power one would need to power an X-ray laser. And it turns out that power scaling is very challenging. It scales as the wavelength to the inverse fifth power. So practically, it means that I can hold a laser pointer in the visible in my hand powered with just a battery. But if I go to a 1 nanometer X-ray laser, it would take a terawatt of power, or a 1 angstrom X-ray laser would take a petawatt of power. Now, a terawatt of power is about the total electrical generating capacity of the United States. So we're not going to build an X-ray laser and have it operate continuously. It's just not possible. And it was this power scaling that is the reason that the first X-ray lasers that lased at a wavelength of 1.5 nanometer were based on a completely different technology, on an electron acceleration technology. And what you can see on the slide is a picture of the LCLS free electron laser at Stanford. It is really tremendous science achievement. But because of the size, the electron accelerator is 2 kilometers long, and the cost of on order of approaching $2 billion, this technology is not scalable for widespread use. So is there another route? Well, we can take lasers where we can build them effectively. The shortest wavelength laser that's now in widespread use is the excimer laser of 193 nanometers, and that's used routinely to print the chips that we have in our gadgets that are used for the recording today, as just one example. But because of the power requirements to scale X-ray lasers, that only gets us to wavelengths in the deep UV at 193 nanometers. And that's why this high harmonic quantum light source technology is very interesting, because it lets us convert lasers where we can make them now and convert them to much shorter wavelength light, spanning the deep UV, vacuum ultraviolet, extreme ultraviolet, and now soft X-ray region of the spectrum, and do that in a tabletop scale apparatus. So this shows just the conversion part. So we take femtosecond lasers where we know very well how to build them in the ultraviolet, visible, near infrared, and mid-infrared region of the spectrum, focus them into a gas-filled waveguide, and then generate light that spans the deep UV, extreme UV, and short soft X-ray region of the spectrum. Now, if you look at the picture on the slide, this looks a little bit like an extension of the nonlinear optics that we all know and love, using crystals to convert light from one color to the other. It turns out this high harmonic generation process is a little different. It's a fundamentally new response of all matter to light, whether it's atoms or molecules or materials, that if we place an atom in the focus of an intense femtosecond laser, the atom will tunnel ionize. The electron is liberated from the atom, or at least part of the electron wave function is liberated from the atom, and then moves in a boomerang path before recolliding with the part of the wave function that's not yet ionized. And if you look at the movie at the bottom of the slide, it's a picture of what the laser field is doing to the quantum wave function of the electron. The electron starts in the ground state, and then due to tunnel ionization, part of the wave function emerges into the continuum where it acquires a different phase than the part of the electron wave function that did not ionize. This gives rise to a spatially modulated wave function and a very rapidly changing dipole moment. And this rapidly changing dipole moment essentially creates a nanoscale quantum antenna that radiates not only the fundamental laser field, but also much higher frequencies, which are in essence what this high harmonic quantum light source technology is.